So today we're going to have a first workshop of the day, which is on the verification of RISC-V core, how to use a formal verification to verify the RISC-V core. The RISC-V is very demanding technology for all of us. So today's session will be very interesting to understand from Sivan how the formal technology can help us to verify the design. All right. So with that, without wasting time, let's have the session. Let's play the video.
I'm Sven Bayer from OneSpin Solutions, and I'd like to welcome you to this workshop on the verification of RISC-V cores. Let's look at what are we gonna do in this session. First of all, gonna look at a little bit the RISC-V side of things, of course, the opportunities and the challenges that come with it. We will then spend some time on applying, in general, formal verification, and in particular, formal verification for processor cores. And after this, spend some time on the really RISC-V specific formal verification automation that we have built at OneSpin. And we are going to conclude with quite a few results on open source cores. So let's jump right into the RISC-V introduction, so to speak, right? RISC-V is an ISA that is highly configurable, lots and lots of choices over the integer register bit width, or even the register number, so to speak, with the E base, and lots of standardized extensions, more and more coming on board, being close to a ratification, and of course also the full claim to fame, so to speak, the custom extensions, because RISC-V is taking care to reserve instruction decoding space and register space, exceptions, and so on for custom extensions. So you can be sure that by using this, you will not break any future standard extensions, which is, of course, is a crucial component in the whole ecosystem. And finally, of course, on the hardware side, all these cores will then have some naming convention based on all the different extensions that are in there. And then, of course, it's by far not only the hardware side RISC-V, right? There's lots and lots of things on top of this ISA level. So you have compilers, instruction set simulator, and whatnot, up to booting Linux on top of RISC-V, which makes this ecosystem so valuable and so compelling for many users. Now, looking at a typical modern design flow, you would start with some kind of architecture exploration to figure out the right split of hardware, software in your particular system, right? You have your particular goals in terms of power, performance, area, or whatever else. And just picking some hardware off the shelf may be not the best way to reach these goals. And in hardware software systems, of course, the boundary between the hardware and software is exactly the ISA, which is, of course, where RISC-V with its high customizability comes into play. And of course, on top of the standard extensions, you have the custom stuff. And below this ISA, on the hardware side, there's still the choice of microarchitecture, which also has quite some impact on the performance side of things, less on the kind of content of the software, so to speak, but more on how does it actually execute. And for your custom extensions, of course, there's several things in general that can be done. You can have new registers or register files, so including increasing the architecture register space of your particular core, or you can add custom instructions. Of course, arbitrary combinations of these two are also possible. So this is kind of illustrated in this picture here, where you have the ISA as the boundary between the software and the hardware, and essentially kind of moving this slider up or down has either more complex hardware with less complex software, or more complexity in software but less complex hardware. And similarly, you have the slider here on the microarchitecture slide, where again, you can trade off lots of things in the different microarchitectures. So the beauty, of course, of this in the RISC-V ecosystem is that this really enables the end users to really just focus on their custom extensions, because essentially the ecosystem is already up and running for all the standardized extensions and extension combinations. So people can really focus on a very small task of customizing such an overall system, of really just doing the custom instructions in their particular core of choice, which means, this is now possible for the guys that are not really the deep processor verification and design experts. Now, of course, there's still also challenges coming with this nice freedom to do things. So you do get to some kind of prototype quality, so to speak, of your core with custom extensions with really low overhead. You can do your performance analysis. But of course, at the end of the day, I mean, you really still need to make sure that your custom extension is working properly. And the working properly actually consists of two parts. On the one hand, of course, is your, I don't know, 10, 15 or whatever custom instructions actually behave as they intend. But also, which you should definitely worry about in this scenario, that adding these custom instructions actually did not break anything of the standard functionality, which in principle means, the verification has to be rerun completely for the core even if you just add a few custom instructions. And of course, to actually meet the strenuous time to market demands that you have in today's world, you really want to build on some decent automation for doing this verification as well, because otherwise it can be a huge effort comparing to actually the design part of the particular custom instructions that you have. And ideally, of course, in the sense of this automation, you would want your custom instruction verification, or rather full core verification, to integrate with your architecture exploration. So to make sure that whatever core configuration with custom instructions you used in your architecture exploration to figure out, this is the thing that really gets me what I need. And just using this in the verification is what would enable a really decent automation, so that verification also becomes as easy as the design part of the custom extension, so to speak. Now let's take a little bit of a look at the role of OneSpin here in the processor verification community. So we have worked on this, what we call processor integrity solution, where the focus is the RISC-V work, which is, of course, still quite much actively in development. We are working in the RISC-V standard organization, RISC-V International Open Hardware, but also working in funded projects. And finally, there's a broad user base of accounts using formal processor verification with OneSpin in general in the automotive industry, and also recently starting up quite some vibrant community around the RISC-V. And finally, before coming to the formal side of things, let's look at the verification in general. So I'm not talking RISC-V specific here. You have your complex architectures with exceptions and potentially custom instructions. On top of that, you have the microarchitecture requirements that pose additional verification challenges, which turns in general processor verification into a high effort task. You not only have to consider instructions, but also arbitrary combinations of instructions to hit all the forwarding paths, and so on and so on and so on. So pretty much everybody agrees that hitting your coverage goals for a processor is quite some work to do in simulation. And this is really where formal nicely complements things, because you can export the formal results back into the simulation master verification plan, so to speak. So if you can't cover all the integrity corner cases in simulation, have the corresponding formal assertions and export their coverage so that you can get to the coverage closure of the overall project quicker. And also, as you don't really have a major overhead of setting up verification environments on the formal side, you typically also pinpoint bugs earlier, so that overall you do end up with less effort on the verification side and earlier bug reporting times, which of course is also important. And the other side, of course, that you get from formal is the exhaustive nature of formal. That a formal proof essentially means the same as if you had simulated all possible combinations. Of course, it is impossible to simulate all possible combinations for anything realistic, but this is nevertheless what the formal result is equivalent to, which means you will systematically detect all kinds of corner cases that you typically would have to be very lucky to hit in simulation, even if you in general have some kind of code coverage goals. And on top of this, what you can get out of this is that there's no undocumented functionality with the formal approach. So ensuring that all other registers, all other instructions do report their proper exceptions, and there's no hidden side effects of doing any weird instruction combinations. So let's now look at how formal actually helps here. And first is again on the effort side of things for formal and the efficiency side. So setting up a simulation-based environment can be quite some overhead. Of course, once it's up and running, you also will be quite productive, but the initial time to get it up and running is considerable. And of course, you want to find bugs as early as possible, because as we all know, finding bugs later in the project cycle tends to be lots and lots more expensive. So that's why formal is a really great addition to such a verification flow, because with formal you have less effort overhead to set things up and have quicker time to fails to debug, typically also easier debug because it's more focused than you have in your typical simulation test benches, which means formal essentially is key in enabling your aggressive time to market goals. Now, how does formal then work in the particular context of processors? So here we have an excerpt of how a load word instruction in RISC-V is described. So you have your standard table for decoding, you have some pseudocode for execution, and then there's a bunch of architecture registers that are specified in the ISA, like the integer registers, floating point, the CSR, the program counter, privilege level, and whatnot. And essentially what this pseudocode is then telling you is how each and every instruction then updates the registers. And it tells you exactly which one it's updating. And of course, the reverse is also true. I mean, all the other registers then are not supposed to get updated. Of course, here stuff like the PC update is kind of implicitly often omitted in these descriptions, but I mean, you get the picture. I mean, you have a full description of what gets updated and what doesn't get updated. And just as a side note, memory for formal is typically modeled then as I/O. So here, essentially, we are not only talking about the update of all the architecture registers, but also the traffic that is produced on the instruction fetch interface or on the data cache interface. And of course, there's not only instructions, the same is true for the exception side of things, right? Exceptions also have a very well-defined way of how they are updating the registers, storing the cause of and the program counter of the exception, and jumping to the exception handler routine, and changing privilege level, and so on and so on and so on. Now, how does this map then to assertions? Here, for the moment, let's just take it as face value. So let's say we have something that is called a state ready to execute. This is something that's more generic than FSMs and also applies to pipelines. But for the moment, let's just look at it. Quite similar to an FSM, right? We have this state where we're ready to execute an instruction. And well, what then happens for an instruction actually to be executed? We need, there shouldn't be a stalling. We need that actually there is something valid coming in from the fetch interface. So these two essentially mean, there is something that is to be executed. And finally, the third part of the condition essentially says, and our ISA model, so the formal model of the ISA, is predicting that no exception is supposed to occur for this particular instruction. And in this case, there's then a bunch of assertions triggering in this scenario. And in this scenario, they're actually then going to verify exactly what we have seen on the previous picture. They're going to verify the update of all the architecture registers and also the traffic that is generated on the data cache. Now, of course, in addition to the instructions, as already illustrated before, you also have the exception side of things, kind of similar looking, right? You also have, there is something that is happening at all, right? So we are not forced to wait, so to speak. But here we have that our ISA is predicting that there is an exception. For example, an access violation or other things like an illegal exception because the opcode doesn't exist. And again, there is an assertion then that will verify that under this particular trigger condition, all the architecture registers are updated according to ISA model, and the data memory traffic is produced according to ISA model, and we are again ending in this state ready to execute so that the next instruction can then start. To kind of complete the case split, of course, you would then also have not only, of course, all exceptions and all instructions, but also the cases where, you are either stalling or nothing valid is coming from the fetch, which is kind of the same, right? It means currently I can't really execute anything. Kind of might call it a boring assertion, but of course you actually need to make sure that in this scenario nothing is really happening, so none of the architecture registers gets updated. Of course, with the potential exceptions of stuff like performance counters and stuff, but none of the normal architecture registers gets updated in this particular case. And this is kind of then completing the set of assertions that you get for your typical standard processor core. And is, as I said before, this idea of this conceptual state ready to execute is much more generic than an FSM state because it really allows for instructions overlapping in the typical pipeline fashion. Again, it's not really within the scope of this workshop to fully explain this, but at least we'll see some papers and user examples where this also has been applied. Now, on top of these operational assertions / operational properties, there's also something very interesting I want to highlight, because essentially what you can get is that you have also the way to run the one-spin gap-free verification, some kind of pattern technology that ensures that the set of assertions that I've kind of hinted at on the previous slide is really forming a model of the design. It is really meaning this forming a model in the strict sense of what is a model, meaning that there is no behavior in your RTL down there that is not explicitly modeled by one of your assertions. So if you find some missing scenario here, it may point out to you that actually you've forgotten to verify a certain instruction or a certain registers, stuff like this, kind of forcing you to really have everything in there. Now, these two things, these operational assertions idea for pipelines and the gap-free, of course, I can only hint at quite shortly in this tutorial/workshop. But yeah, to just underline this is something real and this is working for customers, I would refer to a couple of papers here from other DVCons, so to speak. I guess we have Europe here, we have US here, and we have also DEC. And yeah, you see the customer names here. It's the automotive industry where people are really, really worried about safety critical certifications. So that's really, they are making sure to apply state-of-the-art processor verification here. And yeah, the methodologies with these operational assertions and the gap-free have been applied in these scenarios here. And of course, on top of this, in more the recent years, we have built some automation around this for the particular case of RISC-V, which you can also read up a little bit in this particular publication. Let's now look at a little bit more at how things are integrating with your simulation-based flow. So essentially, I mean, what of course you can do when running formal assertions, you can back annotate the assertion results in your verification plan. It's kind of a straightforward thing, but still you have to make it work for whatever verification planning tool you are using. And you would also want to integrate actually the formal results back into the simulation coverage. So if one of your formal assertions would fail, if you mutated one of the code lines, then you really know that this line is verified by the assertion. And in that case, yeah, you can back annotate this particular code coverage, so to speak, to come from the formal side of things. And in this way, accelerate your overall coverage closure with the simulation as well. Now let's look at the particular automation on the RISC-V side of things. So of course, for an arbitrary generic processor, you would first have to model the whole ISA yourself. And of course, the nice thing about RISC-V, there's lots and lots of things that are standardized. So all the standardized stuff already exists inside OneSpin as a formal model. Now, in order to apply this, we have a design analysis engine, which we'll see highlighted in a little bit. And then assertions are generated. And these assertions are not only covering the RISC-V standard ISA model, but also the custom extensions that you may have added there. And then, of course, you have the standard command line or graphical interface and debug. And as I already indicated, full support for custom instructions and for the debugging disassembly annotation. And all the coverage elements mentioned below actually work here as well. You can integrate with simulation this mutation coverage on the code side, or you could also run this completeness/gap-free analysis. You will get the quick fails out of it, and yeah, methodology and tooling here are such that you typically get unbounded proofs out of it, which is not true for any kind of formal assertions you may run on processor cores. And another interesting side note is that the F and D extensions of RISC-V actually can plug in the FPU verification app as well. So you can also check this a little bit more fancy instructions, so to speak. Now the overall flow looks like this. You fire up a design analysis engine. We'll see that in a moment. You get all the data aggregated inside a GUI where you can then make edits. Of course, you can also do this fully scripted from the command line. So adding your custom extensions, adding whatever implementation info were not extracted by the design analysis. When you then end up with a full database that contains everything pertaining to the ISA of your core and to the verification of your core, which is then used to actually generate the assertions. And at this point, you then have a database of assertions which you then run through the formal tooling to either get your full proofs out of it or your failing assertions and the debug cycles, and of course the integration with the coverage database. Now, how would this look like? So you would fire up the button here to extract the from design. You would then get some status update here, and in particular then highlighted here in blue, for example, the particular standard extensions that are in here. I'm here illustrating the open hardware CV32E core. And under the mappings button below here, you then get lots and lots of details on where and how the complete CSR map is implemented. So which flops implement which CSR fields. Maybe it's a combinations of flops and a few bits tied, or the whole register may be tied to constants, or maybe it's also tied to inputs, not just to flops. So all this is extracted and making for you the setup of this thing a lot easier on your core. And of course, there's other buttons on here for custom extensions and instructions. And if you press the custom instructions button, you would get an additional table that would look much like this. So you have just a name for each of the instructions. You have a decoding that looks pretty much like it looks in the RISC-V ISA manual. No surprises here. And then for the execution, we have picked the SAIL language. SAIL is an ISA modeling language that has been picked by RISC-V International for the official formal model for RISC-V. And essentially here we support a subset of the SAIL expression language for generating then the execution. It's kind of halfway self-explanatory, right? You have let to introduce additional variables, and then you have the usual control flow things and access to register files and so on, and sign extension primitives. In addition, there's stuff in the table like restrictions and debugger. And I mean, overall, this database is actually in a JSON format where the execution part is then in the SAIL format. And then from this table, the full verification is generated, both for the standard instructions and for the custom ones you may have added here. So moving on a few examples. So how are custom instructions then modeled? So for example, you have a memory with post increment. In the decode, you just indicate that a field is used as source and destination register, and then just use it accordingly to read the register, compute the new address, and then assign the new incremented address then back to the destination register. It's also a quick example on the decoding. Similarly here, if it's SIMD, right, again, I mean, just write it down. You have operations for slicing, you have addition, and then you have concatenation here with this add operator in SAIL. And finally, let's say you want to add registers. Let's say you want to do a multiplayer accumulate on a RISC-V 32. So you would add a 64-bit accumulator register, and then have a bunch of instructions around it. And I'm just illustrating here, one of the instructions that actually is reading out the accumulator, or half of the accumulator rather, back into an integer register, which you would then formulate like this. But the key part is just, hey, access the ACC register in here, be it on the left-hand side of an assignment or on the right-hand side, it will just work. Don't really worry about it in any way. So to sum up, it's really straightforward to model custom extensions in this framework, right? You just put in the decoding, and the decoding can introduce new fields apart from the standard fields inside the RISC-V ISA. Can access all the fields from the decoding and all the registers in the execution. Also, the disassembly can reference all the registers. Want to add new registers or register files? I mean, single entry, it's really straightforward. Similarly, if you need more source or destination registers than in standard RISC-V, I mean, just number them and be done with it. Which means that for the typical set of custom instructions, you can really get a highly highly automated verification out of this. And the one thing we are currently investigating in a funded project is how actually to take this one step further. If you already have some kind of formalization in your architecture modeling tool language, to actually get this imported as well into our tooling. Let's look at a few results. 3 of the cores where you can see quite a few results in the open source community is the Core 5 from Open Hardware, formerly known as RISC-V. There's the Rocket Core from the Sci-Fi folks, and there's also IBEX. And yeah, looking at the issues here, there's quite a few related to the privileged spec and also quite a few interesting corner cases for standard instruction execution. And I just want to highlight 2 in this particular workshop, both on the RISC-V core, so the 4-stage pipeline. It's the standard configuration that was the focus of the open hardware work, but last year in the verification. But I want to highlight a few things that were outside this particular configuration. First is the PMPs, so the physical memory protection. So this is supposed, if you have a user mode, so that you can restrict the user mode to have no access rights for certain memory areas. And the specification essentially specifies that the lowest numbered entry that matches an address is the one that determines the access rights, read, write, or execute of an access. But actually, what we have found here is that an instruction gets executed in user mode with a certain address, and entry 0 of the PMPs is matching this address and having no execute rights, but this instruction is still getting executed. The expectation according to ISA here is that it should throw an access fault exception. So I guess in this particular case, there was a later PMP entry that also matched the address and allowed execution of this address, but this, of course, is irrelevant as the first matching one determines the access rights. And finally, something on the floating point side of things. So what we saw when running the verification here is that for some instructions, the result written back to the register file is essentially this off by 1, so not off by integer 1, but off by the smallest unit of representable numbers in the floating point. And what was the common denominator here? These instructions were using the dynamic rounding mode, so the rounding mode from the FRM register. And essentially what was happening, it is illustrated with the convert instruction, but it was applicable as well to other floating point instructions, is if the instruction right in front of it was one that actually changed the rounding mode, there was a chance that this instruction is still using the old rounding mode from before the CSR write, which then, of course, gave the slightly wrong result of the floating point operation. So, to sum up, what we have shown here is a way to reduce the RISC-V development and verification effort considerably. So you do get, by the clever application of formal and automation, quite a significant verification speed up. You can use the formal side of things to accelerate your coverage closure, because of course your overall system will have a simulation-based verification plan and coverage tracking. And on the formal side, you have a quick root causing of bugs, which gives you early bugs and quick turnaround times on bugs. And in this way, it's really a key element in enabling your short time to market for custom RISC-V system. It comes with this high degree of automation. We have seen once this is set up, right? You want to add a new custom instruction. You enter it in this JSON table. You generate the assertions, you run it, and essentially that's it. So all your custom instructions also will have a highly automated verification flow, so very little overhead. And of course, it will take care of not only that the custom instructions are working, but also that you actually did not break anything else. And finally, I mean, this really gives you the full exhaustive formal verification. So it's not just the speed up side of things. You can get really the 100% coverage out of it if you additionally run this gap-free analysis that I was hinting at in the introduction. And in this way, essentially, you make sure there is no undocumented RTL, right? Because, as I said, the gap-free will make sure that your assertions form a real model of your design. So if there's any functionality in your design that is not captured by an assertion, then you will get reports about missing assertions here, kind of forcing you to figure out what is supposed to happen in this scenario and adding then the corresponding assertions and fixing potentially also the gap in the specification. And in this way, you make sure there's really no functionality outside the ISA standard plus custom inside your core. It's only in there exactly what you want in and absolutely nothing else. Which essentially concludes this workshop, kind of closing with a customer quote here from the folks from Silicon Lab that essentially again highlights that this is an approach that is really good at finding corner case bugs. It's good at really pinpointing the issues. It's not something that is talking lots and lots of internals and giving you a hard time with lots of wrong fails. It is really kind of having a look at things that is on the ISA level, and therefore it's really straightforward to figure out that problems here are actually bugs in the design. And yeah, with this, I guess I'm open to questions. Thanks for your time.